Alright, so the next topic is MPLS, multi-protocol labeling switching. Okay, multi-protocol label switching. Now, this protocol is one of widely used service provider topic. Okay, or I can say that a protocol which is widely used in service provider. Now, what the enterprise topic or CCNP enterprise has to do with respective to MPLS. So we don't have a major portion over here. So if I show you the syllabus copy, there are so this particular topic MPLS is being added up on the ENARSI module along with other VPN technologies. Okay, so they say that only describe, there's no lab as per the blueprint. For DMVPN, they say that spoke to spoke, dynamic, IPsec, NHRP, GRE, MGRE, which we have configured and theoretically we have proved. Uh, for MPLS, it's just about describe, but I'm gonna do a short lab here so that we know how does MPLS works. Okay, so most of the things will be discussed theoretically once we have done with the lab. Okay, so before doing lab I would not go and explain each things here because that would make it look little boring and you might lose the track. But let me first give you an overview where exactly this is used or getting used. Okay, so let's say if I have the service provider or ISP. Okay, and from service provider point of view I have a customer A, and let's say there's another customer. So let's say this is a customer A, this is a customer A, this is his branch 1 and this is his branch 2. And on a similar note, let's say I have another customer who has a campus network, and similar way he is having another campus network. Okay, and the cabling is something in this way. Okay, so from customer point of view, that is we guys, enterprise guys, we see always that our edge router or border router, they are told to be connected to service provider. Could be any service provider, Tata or Airtel, Vodafone, Reliance, Orange, Verizon. Okay, so we say that our edge router or border router is connected to so and so service provider, and we don't much bother about what is happening in the service provider end. That's why I said MPLS is not a topic for enterprise point of view, but we just will discuss how exactly the MPLS works. So MPLS is seen here in the cloud or in the service provider area. Okay, nothing from the uh, enterprise point of view. So this guys, they are enterprise guys, they don't see what is happening in the cloud. Okay, the only people who are working in the service provider will be much dealing with MPLS. Okay, fine. So why MPLS now? So how would the service provider look like? So let's say when I have a router, then there should be a equivalent router kept here. Similar way, there will be a router which will be directly connected to this. There would be a router here, there would be a router here. Okay, and we know that we will be forming a eBGP peers on this segment, and so on. We will be forming some eBGP segments on this. What about internally? Internally, there could be multiple routers. So let's say, okay, let me just erase these things. Okay, just making some space so I can draw over here. So what about the internal structure of ISP would look like? So let's say they have couple of routers. So how would this communication would be happening if, let's say, they are all over on BGP? So over here we have eBGP, eBGP. Internally we are running iBGP. Now let's say customer A wants to talk to its own customer A's branch 2 office. So the traffic could flow across on this router, then towards this, and then finally out. Now we call this kind of landscape as IBGP core. Okay, you see the routers are forming IBGP. But what is the biggest drawback of having IBGP here? You need to know IBGP will by default go into the full mesh concepts, and they need to have at least these many neighborship. So you know that full mesh, we have a route reflector, we have the configuration concept to reduce the neighborship, right? But let's say that it's a full mesh. If you see now, if they are forming a full mesh, and how many routers do we have? We have 1, 2, 3, 4, 5, 6, 7 and 8. And if you just do a simple mathematics, so 8 minus 1, 7 by 2, 4. If you just divide this, 4, 7 4s are 28. So you need at least 28 IBGP peer connections if you go with the IBGP relation. Okay, so more number of neighbors, more number of route advertisement happens, your utilization of BGP process increases. So it's not always a wise idea to include the customer network over on the IBGP code. That's the problem number one here. That when the traffic is just between a customer to a customer, which is flowing across or through this service provider, and if he is utilizing his IBGP code, now the traffic is just flowing from one router, one IGP to another IGP, from there to another. But you need to make use of these IBGP configuration. Okay, we know there is a better approach by route reflector and configuration. But again, the biggest question is, why do the customer traffic has to touch the BGP or IBGP network of the service provider? Okay, why don't I create some tunnel, a direct tunnel, so that his traffic terminates here, and then it directly takes that to the existing router, and the router can directly go to the customer A. So that could be a easy task, right? So I can create a tunnel, GRE tunnel, and I can do that, say something like this way. So let's say I have the service provider, I have a router kept on the edge. Let's say I have customer A, customer B, customer A, customer B. Okay, let's say his traffic lands on this. This is called as provider end router, and this is called as customer end router. And even though they have their own internal IBGP core, instead of passing it to this, why don't we have a GRE tunnel? And this GRE tunnel directly connects to an existing router, which will act as another provider end router, and it takes to the customer end, something like this. Now the traffic is just over on this. Agree? So we are just taking out the IBGP here from the service provider. So that is fine. So we know that this can be doable by using uh, GRE tunnel. But now the concept is about MPLS. Why do we get MPLS, okay, in the service provider? So let's assume in this way, if I rule out the GRE, okay, so let's say the encapsulation or the tunnel could have been either GRE or IPsec or any frame relay. So we know that there used to be concept of frame relay. So let's say if we rule out all these things, the leftover option is MPLS, and there's a heavy advantage of using MPLS rather than using any of the tunneling system. Okay, so if I just split this whole MPLS into two components, one being called as multi-protocol and second being called as labeling switching. Now it can actually give more benefits than using these technologies. Okay, multi-protocol represent or resembles that it can incorporate or it can get associated not just with IPs but even with IP v6. It can be used with the Ethernet. It can be used with the point to point. It can used with frame relay. Okay, so that makes it equally usable like how we have GRE and IPsec. Okay, and the second concept that's always added with the whole word multi-protocol label switching. Now we don't need to see the rib to make the decision of forwarding the traffic onto the destination. Now the concept happens on the label uh, lookup. Okay, a label in series like 16, 17, 18 gets associated with the prefixes. Okay, so this kind of labels get associated with prefixes, and that will be put up in a separate table, and the switching of traffic happens. Okay, now you see that we are dealing about the prefixes, but we talk from the switching point of view. So I can just say that they are neither layer 2, they are neither layer 3, instead they are a layer 2.5 protocol. Okay, so MPLS is neither L2 neither L3 because it's making use of a switching technology. It is making use of a prefixes, so we keep them under L2.5. okay, 2.5. So the thing is, the theoretical approach of what this example remains the same. We are gonna take out GRE, okay, and we are gonna replace it with MPLS. So that's the whole uh, basic definition for now. Okay, later on we will do the lab. We will, after the lab I will come back to some more theoretical concepts, but to get started with the lab, I think this particular diagram or this basic definition should be good enough. So from enterprise point of view, the customer don't see what type of cloud they are, what type of cloud the service provider is running. For them is just a EBGP always. Okay, might be EBGP or VPN or DM VPN. That's all from the enterprise point of view. But from service provider point of view, he might use any latest technology. It's all up to him. Okay, so one among them is MPLS, multi protocol label switching, and it's a 2.5 layer OSI model. Okay, so it belongs to that. And to just recreate this scenario, we can use GNS. You just need some routers and you can get this going. Or if you remember, I have already given you a EVNG lab as well. For those guys who want to do it on EVNG, you can just do it on EVNG as well. So if you open up your WhatsApp group, so you can see I have put up a zip file saying that EVNG MPLS CCNP. So you can just download it and you can just all right. So I saw the comment now about the 2 hours of session. Yeah, we will wind it up. Okay. So I had not seen that. So we will wind up this in another 30-35 minutes, and then I have a small topic of another might be 20 to 25, not much. Okay. So we should be good with another 40 minutes. So I've already given the EVNG file over there. Okay, so I'll quickly go demonstrate about this lab. What are we gonna do? So let's say this is my MPLS diagram. So this is whole thing on the service provider ISP. This is my enterprise branch 1. I call it as customer end. C represent customer end to someone who is new to the WAN terminologies, and P responds to provider end. Okay, so this is my branch, let's say some location XYZ, and this is some location 123, and I just want to communicate between these two. So that is from my point of view. Okay, and what would service provider do? They might, let's say they are running a MPLS cloud, so we just configure MPLS. We will see what is the internal components, how does the switching happens, what does label refers to here, how does the labeling get associated to prefix, is something we will check it out in this lab. And that's all from the CCNP enterprise point of view. When you go to the service provider, you will see lot many things. Okay, lot many things. MPLS is not just 1 hour of class. It deals with it's is as huge as your BGP topics. A lot of concepts you have in MPLS, but from enterprise, I'll cover up everything what is being asked in certification and what's been expected from enterprise engineers. Okay, so regarding to this lab, these are customer end. We will run some eBGP here. Okay, external BGPs. Over here, as you can see, we are ruling out IBGP. We don't need IBGP. So what I do is I'm gonna create some GRE tunnel first. But then I'll remove this GRE tunnel and then I'll switch on to the MPLS. And when I switch on to MPLS, we still have the reachability from this customer end to this customer end. So we are never losing our ping response from one customer end to another customer end, even though we have done changes from GRE to MPLS. And once we have successfully done the change and we see the ping is good, we will go to the service side of routers. We will see the different MPLS things that has happened, how the label has been attached, what is called as pop label, how the label gets automatically taken out. Because if you see, for this router and this router, it's a direct BGP, and then you are adding some labels in the MPLS. and that label get recognized between the provider end. And once again, when the same traffic is going out to customer, the label has to be removed off. Okay, so you see that there is some addition of labels happening, and also the deletion of label happens by the provider and MPLS routers, right? So we will see who is adding, on what basis they are adding, and who is removing, and what are the different terminology that's used in the case of MPLS. Okay, okay, so it should load, or might be I will resend you this, because I'm just making use of uh, the as usual devices. Okay, so let me just stop one of them. Okay, so it was might be locked. Let me unlock and see what router image am I using. Okay, so I'm using 7200 nodes. So just make sure you have this image. I prefer keeping the labs logged. The reason is because due to some mouse cursor issue, that the routers can get dragged. Okay. Okay, so I have all the interfaces as you see here. So these are the interfaces: F0 slash 0, fast Ethernet 0 slash 0, fast Ethernet 1 slash 0, fast Ethernet 1 slash 0, fast Ethernet 0 slash 0, and some loopbacks for testing purpose. I would also define the BGP autonomous system, and there is a BGP autonomous system. Okay, so first thing that we would do is configure interfaces. Okay, the interface would be configured first, the IPs, what I mean, and then we will create some eBGP, and we will create some GRE tunnels first. We will see the ping reachability, and then we will take out GRE and then add MPLS. Okay, so these would be the steps. So step number 1 and 2 is configuration of IP address and eBGP. So let's do that. I will follow the previous process of using notepad, write the steps and then copy paste. Okay, because I see that a lot of time when I do it straight on the CLI, students get somehow lost in between. Okay, might be because there are so many syslocks that keep on popping up on the device automatically. So I'll make use of a notepad and then we will copy it. Okay, so first configuration on provider end 1, then we'll do it on provider end 2, then provider, that's the core provider router. We'll go to customer end 1 and then customer end 2. So on provider end 1, let's go to interface fast Ethernet 0 slash 0. I'll say it as IP address of 192.168.23.1.255.255.255.252. No shutdown. I'll move to the second interface where it says F1 slash 0. IP address of one, it's 17.5.7.1 255.255.255.252. No shutdown. I'll create some loopback 1 IP address of 2.2.2 255.255.255. We don't need no shutdown for these software bases of interface because they are always in a up status. At the moment you create, they get into up status. All right, so the next interface configuration on PE2, interface F1/0 IP address 192.168.34 dot it's 1, right? Yeah, it's 1 2. Assign the subnet mask 255.255.252. No shutdown. Interface F0/0 IP address of 27.5.7. Provider N2 is dot 1. Okay, 255.255.255.252. No shutdown. Let's create the loopback 1 IP address of okay. So if you don't see the loopbacks, let me write it over here. So this is 2.2.2.2. This I'm gonna call it as 4.4.4.4. The way I have taken it is, this is 1.1.1.1, 2.2.2.2, 3.3.3.3, 4.4.4.4, and then finally 5.5.5. Okay, in this direction, anti-clockwise. So 1.1.1, 2.2.2, 3.3.3.3, 4.4.4, and finally 5.5.5. Okay, so P2 would be 4.4.4, 255, 255, 255, 255. Let's move to provider end. Here the interfaces are F0/0 IP address of 192.168.23.2 No shutdown. Interface of F1/0 IP address of 192.168.34.2 255.255.255.252. No shutdown. All right, then loopback, we just can create it as 3.3 series. Okay, we'll move to customer end, enterprise customers. So let's say interface F01/0 IP address of 17.5.7.2 255.255.255.252. No shutdown. Interface loopback 1 IP address of 1.1.1 255. Okay, let's go to enterprise customer 2. So interface loopback or fast ethernet 0/0 IP address 27.5.7.1 255.255.255.252. No shutdown. Interface loopback 1 IP address of 5.5.5 255.255.255.255. Okay, so this is the basic interface configuration. So once we are done with this, I have to enable some routing protocol on the cloud side. Okay, so for that I would prefer going with OSPF because we are good with that. But yes, service provider has an equivalent protocol which is called as ISIS. They are very equivalent, ISIS and OSPF, but since we don't have this, so I'm gonna prefer using OSPF between these three routers. So I'll just advertise them. So let's say router OSPF 1, and I'll advertise the networks 192.168.23.0.0.0.0255 area 0, network 2.2.2 2.0, or and then I'll advertise 255 area 0. So this is something which should be repeated on all these provider and routers. Router OSPF1 network of 192. Okay, so P2 will have 168.34.0.0.0.255 area 0, network. What is the loopback here? It's 4.4 series. Okay, since I'm making use of a single IP, I can also advertise it in this way. Okay, so that will also work for me. If you see them, this is as good as this because I'm using a single IP. So let me do the same thing here. Okay, 2.2.2, and I'm advertising it on /32 and area 0. Okay, over here we have three networks that gets advertised. Okay, so the first network would be 192.168.23.0 series network. The second would be 192.168.34 series network. The final would be the loopback network. Okay, on customer end we don't need OSPF because we don't have multiple routers. So what is the point of keeping OSPF here? Okay, so from service provider end, the LAN communication between three routers, we have OSPF. Now we will enable some communication happening between this and this, customer end and provider end. So we know that eBGP is a best suit here. So I'll enable eBGP between customer and the service provider. Okay, so we are going as per the real time scenario only. I'm trying to consider all the real time scenarios. Okay, so how do we construct the BGP configuration? So we know that from enterprise we would be doing the setup, and from customer, I mean from provider end or service provider end, they will have their own engineers. But this is a lab setup, so we have to do it on both the side, both the routers. Okay, that is customer end as well as the provider end. So first let's do it for provider end, P1. So I'll say that router BGP, and what is the provider autonomous system here? It's 65,000. I'm gonna define my neighbor statement. Neighbor is located at 17.5.7.2. Remote AS. What is his remote AS? It's 33,000. Right? That's the remote AS, right? Okay, fine. So we don't need any network to be advertised here. We just need the routers to have a eBGP relation. So these two lines are sufficient to have a eBGP. Okay. So let's finish off for P1 and C1. Okay. So I'll just copy and keep here. But now the AS number would be 33,000 on the customer end. If you see over here, right now I'm trying to configure this part. Okay, I configured this, and now I'm moving on to this configuration. So it's router BGP 33,000, remote AS is sorry, neighbor is located at 7.1, and his autonomous system is 65,000. Okay, okay, time to configure a similar configuration on provider end 2. So router BGP. Now what is the autonomous system? It's 65,000. Neighbor statement says neighbor is located at 627.5.7.2. Remote AS of 55,000. I'll copy this, go to customer and 2, and over here my autonomous system is 55,000, neighbor is dot one, and he is located at 65,000. Okay, so I must have all the IPs configured along with the eBGP peers, and there should be a OSPF in the service provider cloud. Now the ping should be successful. Okay, so the normal ping once again would follow this path, because we have not done any fancy thing so far. It's just a normal end-to-end connection. So the ping packet would travel in this direction, right? We have eBGP here, so we are good. We are forwarding the traffic till here. Between these three routers we have OSPF, so they will forward the traffic, and then there is again a eBGP, so we should have the ping following this direction. But as I said, we don't want a customer traffic should enter to the service providers, uh, should follow the service providers backbone. We can call it as a backbone, right? So what I do is I just create some GRE tunnel, so that my traffic, instead of going on the backbone, just make use of an exit path and take up the exit path, something like this. Traffic should be like this. Now then, I told you, why GRE tunnel? Why don't MPLS? Because MPLS can do the same thing what a simple GRE could do, but along with that, it can do lot many things of labeling packets, uh, keeping its own cache memory, faster switching process. Okay, there is no need of such a heavy header, because MPLS don't take uh, header size as much as GRE or IPsec. So there are a lot of advantage, including MPLS. Okay, and the decision is not made upon the rib now. They are made upon the label table. So there will be a different table that gets generated, and that's called as label table. Okay, so let me paste all this config which we created. So where are my terminals? Okay, so let me take them in a serial. Okay, I can do that, right? Okay, so first C, then P, then P, then P2, and then at the end C2. Okay, C1, P1, P, P2, C2. Okay. I don't know why it says press enter to get the prompt. edit. This is very strange.
Narrator dialog. Close. Narrator exiting narrator.
So anyone know any shortcut on this? What is this? Secure CRT? Press enter to get the prompt, which usually don't ask for, but I don't know why is it asking. Okay, so looks like that those instances are corrupted. Yes, so those are corrupted, but what I'll do is I'll just quickly recreate the same thing. So we need 2 plus 2, another 4 routers. We can keep the fast Ethernet interfaces. Okay, so they are somewhere here. So we can label them. So this is 0/0, 1/0. This is 1/0 once again, and then finally 0/0. Okay. So let me try to stop them. Okay, something like this, and this we can just get rid of them. Alright, now let me try to start them all. So these EVNG guys says that once you deploy some new nodes, it's always wise enough to wipe them. So I'm gonna just follow their best practice, and then we can take the CLI of these. So console to all nodes. Okay, for some reason if it doesn't come, then you have to manually trigger them. So something like this. So we are missing out that host name, right? I'll also tell you how do we do that. So while deploying, if you can just rename this, you can just change accordingly. Okay, so this is CE2, you can call this to be CE2. So it just changed its name so that you can easily practice, and you have all the host name just visible on the topology itself. Okay, so for some reason I think I had not put the host name, but since we have now deployed new routers, so I'll make a additional command or additional lines. So guys, I'll give you this topology after the class. Okay, might be the previous one might not work for you as well. So I'm gonna copy the first one, and okay, now there is a confusion because all of them are labeled as same. So now what I need to do is I have to open one after one. So I'll first open up this. See, this is why I locked them. So this is my P1. Let's say no. Let me paste the configuration. So there comes the first router. Let's go to what's the second config for. So second one is for P2. Okay, so say no for initial configuration dialogues. We would like to prefer doing it manual config. Okay, what do we have next? We have P edge or P router. And then moving on to the last router. Okay, so where is my customer end? So this is my customer end. Let's see roughly some of the show output. Show IP int brief. So I have one physical IP, one loopback. What about the routing table? So I don't have any routing over here. What about the BGP neighbors? Okay, so they are forming eBGP with this provider edge. Okay, and this is my second customer router. So up and up, show IP BGP summary. Okay, so neighbors are not up here. All right, so it says that there is some duplicate address. 25 5. Okay, so should be a problem with. Okay, so these are not dot one, these are dot two. Okay, I've kept dot two on customer and dot one on provider end. That's how even in the real time they follow. The provider end will have the dot one, and then the customer end would be dot two, or any number, but it could be it will be always like minus one kind of thing. In the sense, provider end will have a smaller digit than a customer. So let me change that over here. Okay, so now they are up. What about on the provider ends? So we have some IPs. What about the routing tables? We have the OSPF learned routes. Okay, so let's see if I can reach to another end. So this may not work because we have not advertised any networks over on eBGP. We should have done that. But anyway, we will proceed with the MPLS lab. Otherwise, we will just be lagging with all the different routing concepts. Okay, so we will focus on the MPLS here. Okay, I'll do one thing. That is, so what is the configuration right now? Okay, so let's advertise the network here. Okay, 1.1.1 mask of 255.255.255.255. Router BGP 55000, network of 5.5.5, subnet mask of 255.255.255.255. Show IP route. Okay, so this network can be now seen on the provider end. Okay, show IP route. So we don't have anything here. The reason is we are not advertising back from the provider end. We just advertised uh, only on the customer end. Okay, so we don't have any network statement over here. That's why there's no reverse communication. So we should have advertised all these networks. So as of now, they're just forming eBGP enable from MPLS point of view. Okay, so we have the basic configuration. So let's create some GRE tunnel between these two provider ends, so that the core router is not being engaged for customer traffic. So we can just use this exit path from customer end 1 to customer end 2 without going further. So for GRE tunnel, we'll use P1 and P2. Okay, so on P1 I can say interface tunnel 0. I need two things for GRE. One is tunnel source and tunnel destination, two important commands. So source here is 2.2.2 and destination here is 4.4.4. The loopbacks of P1 and P2. Okay, so loopback of P1 and loopback of the P2. And then let's define some IP address to this tunnel. So let's say this is 192.168.24.2, 255.255.255.0, and the same config goes for P2 as well. Interface tunnel 0, tunnel source of 4.4.4, tunnel destination of 2.2.2, and IP address of 192.168.24. Okay, so let's give some IP. Let's say 24.4 or 5 or something, because they are class 24. Doesn't matter. Don't have to be next to next IP. Okay, so this is a class 24, so we can just give any random IPs. Okay, now uh, now since I'm creating GRE tunnels, okay, I'll be also enabling the IBGP. So IBGP will be constructed over on GRE tunnels, so that we have a end-to-end communication flow. Okay. So once we have the GRE tunnel, I would like to create my IBGP, that is that's the communication between this and this over on IBGP, but I would be using the GRE tunnel header, because that is what we said. If I just make IBGP on this cloud, then we know that the neighborship will be of this order. We don't need that. That's why we are taking out IBGP and providing GRE. Okay, so it's either way. You first create IBGP and then add the GRE tunnel, or first you create a GRE tunnel and then advertise the IBGP on this. So ultimately we just need end-to-end connection. So we have IBGP, which is acting as routing, and we are providing GRE tunnel, so the traffic just move on this direction itself. So for IBGP, once again, it's just between P1 and P2. So let's say router BGP 65,000, neighbor statement 192.168.24.4, remote AS is again 65,000. I'll define the neighbor with the P as well, or not with P as well, but I'm just gonna say that next hop self. This is from IBGP concept point of view. Okay, next hop self. So same thing on P2 as well. So 24.2 and 24.2 next hop self. So you know what happens in IBGP, right? In case of IBGP, when something comes in this direction, what this IBGP router does is, by default they keep this as next hop gateway. Now that can lead to issues if we lose the connection. If we lose this router, so all the existing route will be just uh, losing its connectivity to this. Now what we do is, we just stop this feature, okay, and we add an additional command called as next hop self. Now this router gateway IP is being advertised to the further routers. So if a network over here, if you just open it, this will show the next hop as this, no more as something which is on a far end point. Okay, so that is the next hop concept of especially in IBGP. Okay, not in EBGP. EBGP will change accordingly, but IBGP have a tendency of keeping the far end itself, and we don't want that far end, because if there are multiple IBGP routers here kept something like this, why do you think this IBGP should know that this has a gateway IP? Doesn't make sense, right? Next hop, because in intermediately there are a lot of other routers, so you would prefer keeping this as the next hop, not this one. So we just change that properties. Okay, so these are few things. Let me add them and bring the IBGP over on GRE tunnel. Okay, let me do one thing. Let me first add IBGP first. So let's see if the IBGP neighbors have come up. Do show IPBGP summary. Okay, so it says 24.4 never. So why is that? All right, so that's because GRE tunnel interface is not being applied, right? So GRE has to come up. So this is the config on the first device, and this is the config on this. So we are creating IBGP on over on the tunnel interface now. So now the BGP should come up. See, BGP came up, okay? And now we can see a new prefix on our customer end. So we see 5 series network is visible. And if I just try to ping, so we should have pinged it over on the loop back. Okay, so I'll add loop back here, so we can ping that. Let's see the flow now. So this is trace route 5.5.5. We need numeric. Do we have source? Yeah, source we have. We have loopback 1. So what is the flow now? So it says it's going. So when I'm pinging to 5.5, let's see what is the flow. So it's hitting up this interface 7.1. Then it's going to the GRE tunnel 24.4. That's nothing but this dot 4. And then it finally appeared to the 7.1. So the traffic is going this way. So we have isolated the backbone concept, so we don't engage anything on this side, so that's good. We are making use of GRE, and we have end-to-end connection, so this is doable. Okay, this is doable until MPLS was being launched few years back. But once MPLS was launched, it was seen more beneficial than GRE, and that is what is this whole lab about. Okay, so is my screen lagging? I mean, is there any problem with the screen and the audio not being matched up? So let me see if I'm having any latency. Okay, so looks good only. All right, might be some temporary glitch. Okay, So you see the path is going via P1, GRE tunnel, P2 and CE2. Okay. Uh, Now we need to introduce MPLS. We need to introduce MPLS by taking out GRE tunnel. Okay. So what I'll do is I'll put a quick no here, so that we are taking up. Okay, might be you need this later on, right? So I'll just add up here. So this will be put up in the workbook, but I'll also give this notepad after the class. Might be if you want to add something and try something on your own. Okay, so we will take out this tunnel. We will take out this tunnel, and from the IBGP concept, we will take the neighbor command, which is pointing to the tunnel. So these are the no commands. Okay, and the additional commands here would be on P1 and P2, that we have a IBGP on a physical interfaces. Okay, so I'll go back to router BGP 65,000, and I'll say that now neighbor should be on 4.4.4. That's nothing but the loopback address of P2 65,000. I'll say neighbor 4.4.4. Since this is over on loopback, so we know that there is something called as update source loopback 1, and then we will say this is a next hop self. Okay, all from our BGP topics, and these are additional on this as well, but we just need to change the IPs. Okay, so first let's do a no on these interfaces. I'll go to P. Where is it? Okay, so one side of tunnel interface gone down. Let's do it on the second side as well. I'll take out the neighbor command, as well as I'll take the neighbor command from P2, and then we'll add the additional or the new sets of command required for MPLS. Okay, so all EBGP, IBGP are up. Okay, so this will not come up because we have not advertised P in between. Okay, so we were using GRE earlier, so that we could isolate the backbone code so that our traffic don't come here. Now what we'll do is we'll, instead of GRE, we are enabling MPLS. So let's enable MPLS. Okay, so the command to enable MPLS is, okay, once again I'll make use of notepad instead of doing it straight away there. So I'll go to P1, I'll go to its interface F0/0, and this is the command which will enable MPLS protocol. Okay, so the same commands to be put up on all the routers. So let's say the P router, P core router interface F0/0, MPLS IP interface F1/0, MPLS IP, P2 interface F1/0, MPLS IP. Okay, so all these interfaces which are pointing to the service cloud or service provider, no changes required to those interfaces which are facing still to the customer. So no changes here. Okay, they're good. We just need MPLS to be enabled on this path. Okay, so once we have this MPLS enable, I will show you what do we get exactly. Oops, okay, so that was not the config of P2. So this is for P2. Okay, so this is something comes up, LDP, label description protocol. Okay, so since I just misplaced the config, I had to just remove it from P2. So these are the config which we enable. We can see something is started showing up as LDP. Okay, label description. So let's see what is happening here. If I go to my C2, if I try to ping 1.1.1, if I say the source to be 1, it's pingable. Okay, and it's reachable, but you need to note that uh, we don't have IBGP still on this. Okay, we just have MPLS on all of them. So now these communications are happening over on MPLS, not over via IBGPs. It's happening over MPLS. We will see part by part now. Okay, so to see those things, I mean, to make sure that there is no intervention of the provider or the backbone core for the customer to customer traffic, what I can do is I can quickly check in the router P whether this is happening over on the legacy BGP IBGP point of view or MPLS. Okay, so I can see show IP routing table. Okay, so there is nothing for 1 series and 5 series, which is customer network. I can make use of the chef table as well, Cisco Express forwarding. So there is nothing for 1 series and 5 series. You can go with 1.1.1. It says no route. If you do 5.5.5, it says no route, but still we can ping to each other. Okay, we can ping the way we want it. So P is not never been bothered now. P is not getting utilized. Okay, so what is happening here is now we need to check the labels. We don't see the routing tables, so routing table is gone out. Now let's see from the provider end 2 point of view, what is the traffic flow for 5.5.5. That is, from this router I'm trying to see what is the path that's been taken up. So is it going via this, or is it going via some other way? If I do show IP route, it's showing me that it's been known via 65,000 BGP. There's some tag added. I mean, that's nothing but the autonomous system of customer end. We see 4.4.4. Okay, MPLS label none as of now. Okay, so this is 4.4. Series. So 4.4. is nothing but this router. So it says that 5.5.5 series of IP has been read over from this point of view. Something like this. Okay, now what I'll do is, since we have the MPLS configuration, I'll make use of the MPLS table called as MPLS forwarding table. There will be a parallel table generated as soon as you have MPLS, and over there we will see all the interesting things. So to reach 5.5.5, what exactly has happened is, so you can see the labels been getting associated now. So usually MPLS label starts with 16. Okay, so don't ask me why they start with 16. That's how they start. They don't have 1 2 3. They start with 16, 17, 18, and something like that. Okay, so they start with 16. That's why we see them. The label is pop label. I'll tell you what does this pop label refers to. It says 3.3.3/32, which is nothing but the loopback of this. Outgoing interface 0/0. Next hop 23.2, which is this one. Okay, so we don't see this under now the Cisco Express forwarding or routing table. Instead, we can see the MPLS label has been taken up, and then we see 17 to 17, label of 17, outgoing interface 17. That's for this direction, this communication. Okay, for this, it has set a local label 17 and outgoing label 17. The tunnel interface as 4.4.4/32. Outgoing interface of F0/0. So that means traffic is going once again on this, but you see there is a label which is occurring, which has been taken care here, and it says 23.2. So basically something like this. And then 18, the label number 18, which says once again pop label, and now it's to the 34 series of network, that is to this network. Okay, from this router to this network, MPLS added label of 18. Outgoing interface is in this direction. Next hop is this interface. So this is a MPLS table now for the communication which is happening internally. Okay, so we will not get more info on the routing table here. So routing information will be now avoided. Okay, and if you just open up your routing table here, so you will not see anything for the customer end networks. So let's see the same kind of observation on the provider end too as well. So if you see, if you remember, we did see the chef table for 5.5.5, which said no route on the backbone router. If the same command, if I execute on the provider end, it says that the next hop is 27.5.7.2. So that's okay, not that, that's going to be this one. Okay, so when you open the Cisco Express forwarding table here, you see that it's saying that 5.5. Series network is being read here. Okay, and okay, I think there is a missing label here, so let me see. Okay, let me check it out for 1.1. Series. Okay, now the interesting thing you see here. So there is one more observation you need to do here is when you're executing this command, when you did for 5.5, that is directly connected, you see no label. Okay, and when you at the same time from the same router, when you do it on a far end customer end, you see a label, right? So what is happening here is, as I told you, the customer routers do not understand what are labels. So it's a work of these MPLS router to remove the labels before passing it on to this customer, because they are purely eBGP now. They do not understand MPLS. So MPLS is just in this service provider. Okay, but at the same time, the same router, when it receives something for a MPLS traffic, its work is to add a label as well. So that's why you see in one scenario it took out the label, on other scenario it added up the label, and that label is now contributing to your MPLS tables, and this table is parallelly running along with your routing table. Your routing table don't get looked up, no more routing table considers. That's why we didn't see anything falling under on this router. Okay, it's all MPLS and it's all about labeling. So what happens is that traffic which is going on this direction, this router is gonna add a label, it's gonna send it, the label will swap. Okay, we call it as label swapping. So 16 will get to 17, then this router will swap it again, 17 becomes 18, and then this router will finally delete the label and send it to the customer end. So that's how the traffic in and out happens. Okay, so let me show you the MPLS table on this side. So the 16 is the one which originated for this, for one dot series. You see 16 got added up, and we are pointing it to 2 dot 2 dot network, or 2 dot 2 dot loopback, or whatever. So this is 2 dot 2 dot. We said 1/0 is my outgoing traffic or outgoing interface, which is hitting on 34.2. Okay, so let's see what is happening on the provider end for the same command. So label of 16, pop label is nothing but whatever label you just sent to P is deleting it, and whenever it deletes, it add up the tag of pop label. Pop refers to delete. Okay, so we see that 16 label is removed or torn off and then sent to the next router, that is PE1. So let's see, show MPLS forwarding table. Okay, so this is deleting of labels. This is called as adding of labels. When you're passing some information to 2.2 network, you're adding something. When you're receiving when you are deleting something, you call it as pop labels. And from provider end point of view, it has nothing to do with addition. They are just removing the IDs or removing the labels and sending it across. Okay, so what is happening here is, so when the router P1, okay, so let me see here. So when a P router 2 receives something which is to be forwarded on to 2.2, it's going to add the label 16. Okay, and whenever you see something as pop label towards 3.3.3, which is my provider and this 23 network, we are gonna remove the label. So that is how this MPLS router works. So if something is going out over onto this network or this interface, it is gonna always add something. Whenever the traffic is meant for this networks, it's gonna remove the labels. That's what that table is referring to. Okay, so if there is something which is destined for this destination, you will add these labels, and the labels are to be taken out. Whenever you're trying to send something to 4.4 something, then you will add that particular label. Okay, so you see here, when I triggered this command, it labels with 17. When I trigger 1.1.1, it labels at 16. It could have labeled at 17 itself, right? If you would have thought that might be label 17 is the default number, but that's not. Okay, so the router will make its decision. As soon as you have MPLS, they are gonna construct some kind of table, and it usually starts with 16. That's a default behavior, but then the numbers can change. So in this router, 17 is getting added up whenever the traffic has to be labeled and sent, forwarded further. If something has to be forwarded to these two next hop, they are meant to remove the label and send it. That's what the meaning of this table is. Okay. Okay, now since we have done this lab, I'll come back to the theory. Theory has few terms now where your doubts would be cleared. Okay, now since I have not run any sorts of packet tracer, I'll first run the packet tracer and I'll show you few things here. So let's capture some traffic here. So using Wireshark, I can show you that these are 2.5 protocols. Okay. Okay, so I have some strange problem with the default one, so I have to make use of HTML here. Okay, so luckily the hashtag is getting started up. That's a good thing. Yeah, so I can see some packets, right? If I just click on one of them, let me just stop this. Okay, they are stopped now. If I just click on one of the ICMP traffic, let's first see what are the things we see here in the Wireshark. So we have some LDP. LDP is, do you remember the, as soon as we enabled MPLS, we got some protocol enabled, LDP, right? So we'll talk about LDP. So these are our ICMP traffic. OSPF we do see because we are having OSPF in the core, in the service providers IGP protocol. That's, we are not interested to see that. Neither we want to see the BGP packet as of now. So let's focus on LDP first. I mean LDP and ICMP, which is of important. Okay. First, let me show you what ICMP is actually carrying. So ICMP traffic is our ping packet from customer 1 to customer 2, and on the top we are having MPLS and we are capturing the Wireshark. So definitely the ICMP is now flowing inside MPLS, right? So that is why we can see the MPLS header is added here. Okay, so this is ICMP packet, and we do have MPLS because that's how the traffic path is right now. And if you see now, we have a L2 header, OSI data link header. We have OSI's layer 3 header, and in between 2 and 3 we have MPLS. That's why I said MPLS is layer 2.5. Okay, so I hope you can see on the screen. So this is layer 2, this is layer 3 IPv4 header, this is the data, ICMP data, and then in between we have the MPLS. And if you just elaborate the content of MPLS, so we see things like label, experimental bits, bottom of label stack, MPLS TTL. Okay, so all the protocol will have some TTL values, right? So this MPLS header, if I just try to draw it, okay, let's say this is a header and we call it as 2.5. Okay, so the first uh, component here would be label value. Okay, we have something called as EXP, experimental bit. We have something for S stands for bottom of stack, and finally TTL. Okay, so label value, which is nothing but 20 bits. The next experimental bit is of 3 bits, and the stack or bottom of stack is 1 bit, and TTL of 8 bit. Okay, now what is label value? So label value is whenever you're gonna carry the value of labels. Okay, if I just open up this Wireshark, so do you see the label value? It says 17, right? We saw different types of labels. We saw 16 getting added up, 17 getting added up, 18 getting, and so on. So that's the component. This is the component of 20 bits which carry the label. Okay. What about the next component, EXP? So EXP is nothing but experimental bits. Okay, now if you see the MPLS label 17, you have to check this binary numbers, but I'm not going in detail because we have discussed, or I think I pre-assume that you would know this. So this is all to the power 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and finally the end result is 18. Okay, so how many bit size is this? This is a bit size of 20, right? So you just can calculate these numbers. So if you see here, this is a block of 4, 4, 4, 4, and 4. And if you just do count them, they are 20 bits. 20 bits, the value is 17, and you just convert into the binary numbers, you get this conversion. Okay, that's why I have written on my diagram that it's a 20 bit. The next is 3 bits. That's why only 3 binary values, and it says 0. Okay, why? What does this experimental bit carry the information about? So it carries the information like QoS. Okay, for QoS there could be some IP precedence values that's stored and required in the MPLS traffic, which is kept here. So since we don't have any QoS, so there was no value stored, and it was taking the blank space of 0. What about bottom of stack? Okay, so it says it's a 1 bit, and where's my Wireshark? It says 1. Okay, it says 1. That 1 is nothing but it's a number of labels that it's carrying right now. So number of labels carried. Okay, there could be scenarios when the labels are one or more. Let's say you have two labels carried at a time, 17 and 18. So you will see the number would have changed to 2. So usual case they will remain 1, and you will see most of the time bottom of stack representing as 1 itself. MPLS bottom of label stack as 1. Okay, but for some MPLS VPNs or it's possible to add more as well. So in that case you will see the number get incremented. Okay, so that's about bottom of stack. And TTL, as we know, it's a time to live, which is nothing but when the MPLS packet from a router to another router, when they switch, they basically get decremented every hop. So that concept still remains the same, that when they forward from a router to router, or when we do a trace route, they decrement by 1 from one hop to another hop. So that makes the total header of MPLS. Okay, and hold together this, if you just calculate 20 plus 3 plus 1 plus 8, how much is it? It's 32 bits. And if you remember, 1 bytes equals to 8 bits, which make this to be 4 bytes, right? So so 1 byte equals to 8 bits. 1 into 8 and 32 into x. If you do 32 into 1 by 8, it's a 4. Okay, so I can say that this whole header size was a 4 byte, or in bracket 32 bits. And also remember, the header is added in between the layer 2 and layer 3, so that's why we call it as 2.5. Okay, now regards to some of the terminologies in the MPLS concepts. So we call this to be CE, which is nothing but customer end. We call this as P, which is nothing but provider end. We had a router called as P, which we referred as provider core or backbone. Okay, once again, this is provider end, this is customer end. And also these routers, especially the provider end routers, we also call them, because these are the router which add the tags, right? Whereas this just removes or deletes the tag. So the router which adds the tag, we can also label them as LER. That's called as label edge router. Okay, same goes over here. We can call it as label edge router, LER. And then the provider which are deleting those labels, or they are switching the labels from this sends 16, they switch to 17, might be this sends to 17, they switch to 18. So basically provider is more or less doing a work of switching. Okay, they are basically doing the work of deleting or switching the labels. I can call them as LSR. Okay, not sure why the pen is giving this. Give me 1 second. So we call this as LSR, label switch routers. Okay, switch, label, and routers, LSR. Okay, so finally, I have almost done. So I have something for label push, label swap, and label pop. So label push is when we add a label to packets. Okay, so basically these edge routers do the work of adding the tags. Label swap is doing the work of replacing a label with another value. Okay, your provider or the backbone does that work. And finally, label pop is deletion. Okay, so removing the label before sending to customer, and once again done by the edge MPLS routers. So if I just have to take my screenshot. Okay, so let's say I take this screenshot. If I, okay, I can just make use this itself. And if I just have to label what is what, so we can do that. So let's assume, okay, so let's assume the packet flow direction is in this direction. Okay, so what happens here is we have uh, push labels. That is, packet gets added up with the MPLS label. When you forward it to the core, they will swap the label to another value, and then they send it to the edge router. Okay, now this edge router, they do the work of pop label. That is, deleting of the label and then finally passing it to the destination. And when the traffic comes here, they are without any MPLS labels. Okay, so before I wind up, there's one small thing which I want to tell, which ends up the complete MPLS. That's called as LDP, which we have seen at the start of this lab itself, but had not theoretically discussed, which is called as label distribution protocol. So basically what happens here is label distribution protocol, they gets exchanged between the routers. Okay, they get exchanged between the routers, uh, and each router will generate some labels locally, and these prefixes are advertised to each other. Now, how do they form agency, and how do they keep alive? So there's a concept of LDP hello. As like you have your hello packets in OSPF, which makes a neighborship connection. So these LDP also form some sorts of neighborship using LDP hello. They are unicast in nature, and we call them as a neighbor adjacency. That's the reason when you check the Wireshark, we could see LDP hello messages. Okay, so we could see a lot of hello messages, keep alive messages. So these are the protocol which do the work of label that's locally generated to be distributed among the routers. Otherwise, how these labels will get exchanged if there was no such protocol? Okay, so make sure that they are UDP in nature, and they are the hello packets will follow the multicast. This is for LDP's hello packet. Okay, so I think this I'll just redraw this once. So let's say I have two routers. So first they form neighbors. That happens over on unicast. Okay, and then the sequential hello packets, or LDP hellos, they happen over on multicast. And the main work of LDP is to exchange label information. Let me see if I do see something here. We have hello message, keep alive. Okay, so what all the components we see here? We have some uh, LSR label switch router ID. So whichever router is adding the IP address. Okay, like how we have the router IDs in OSPF, similar way LSR. So that's a label switch router which is adding the identifier number. The same concept of highest loopback gets elected, or highest physical IP gets elected for LSR to be counted. And these are all UDP packets on port number 646, and the multicast IP for LDP is 224.0.0.2. If you remember, this was being used, I think, in HSRP as well. HSRP version 2. Version 3 was 102, right? So let me just cross verify. Yeah, so you can see this. Okay, so LDP, label distribution protocol, LSR, label switch router. What else we have? LSR, label switch router, LER, label edge router, customer edge, provider, label push, label swap, label pop. So pretty much all the things we covered from the enterprise. Okay. So it was just a describe. Since we went with some practical, it took some extra time. Okay. Otherwise, it was just a theoretical concept in CCNP. All right. So let me know if you have any doubt. I am not gonna take IPv6 today. Might be I'll take tomorrow. Okay.